All right, Algebra 1, Lesson 12, using properties of real numbers to simplify expressions. Now, before I get too far in here, you guys got to remember that tomorrow we are reviewing. Friday is your test, right? Okay, so if you haven't looked at the review yet, right, that's kind of silly at this point, right? Okay, so you should have at least looked at it. You should, before tomorrow, have the whole thing worked out, right? Okay, so let's get into this because tomorrow we're going to grade and then we're going to review. Okay. All right, so we have the properties of real numbers are used to simplify expressions and to write equivalent expressions. Okay, meaning, we can have an equation on either side of an equal sign, two things set equal to each other. What our table that we're going to look at is going to show properties of addition and multiplication when A, B, and C are real numbers. And I'm hoping that all of this is fairly review for you. Like the identity property of addition means that if I add 0 to something, I'm going to get the number that I started with. So if I take 5 plus 0, I'm going to get 5. Identity property, okay? I get what I started with. The identity property of multiplication means I'm going to multiply by 1 and get what I ended with. That's what we mean by identity. We're not changing the identity, okay? So in order to not change the identity with multiplication, we multiply by 1. In order to not change the identity with addition, we add 0. Okay? All of that makes sense? Familiar with all of that? Great. All right, then we have the commutative property of addition, which means that so long as I'm only working with addition, that I can move things around, right? I can change the order of the equation so long as I'm only working with addition. Okay? Any problems there? We got all that. Okay. Multiplication works the same way. Multiplication is commutative in most cases. Now you'll find out in Algebra 2 there are some situations where we can't use commutative property of multiplication, but that's whenever we get into matrices and those types of things, which is understandable. You'll understand it when you get there. Okay, then we have the associative property of addition, meaning that I can change the association with a set of parentheses. Meaning that, just because something is to the left, if I put if I put parentheses around it, according to order of operations, I have to do that addition first, right, and then add whatever's left. Okay, so just means I can change the association, and that, again, because commutative property works, the associative property also works with multiplication. Anything in there that is new that you feel like needs explanation? No? Okay, and that's for the most part, that's what was in your textbook. So let me see. Let's look at some questions here. Okay. Which property of whole numbers is illustrated by the statement 40 times 48 equals 48 times 40? Can anybody tell me what property we're using? Tiffany. Commutative property multiplication is exactly right. Okay. Let's look at number 2. We should be able to kind of fly through these. Let's see. Christian, which property of whole numbers is illustrated by the statement 18 times 1 equals 18? Identity property of what? Identity property of multiplication. Very good. All right, that should be fairly easy. We're seeing multiplication, and we're seeing that we are getting what we started with, which was 18. Okay? Jeremy, which property of whole numbers is illustrated by the statement 6, parentheses, 6 plus x, close parentheses, plus y equals 6 plus parentheses, x plus y, close parentheses? Associative property of addition is correct. I feel like a game show host. Classify the statement as sometimes, always, or never true. C plus negative C equals D for D equals 8. Let's see. Sometimes, always, or never true. What do you think? What happens if I add C plus negative C? Turns to 0. Does it matter what I plug in for C? No. And if D equals 8, will C plus negative C ever equal 8? No. So is that always, sometimes, or never true? Never true. Very good. All right, number 5. Which example shows the associative property does not hold for division? All right, let's look at A, for instance. Let's see. We've got 24 divided by 3, right? What's 24 divided by 3? 8. What's 8 divided by 2? 4, okay? In our next set, on the other side of that, on A, we have 3 divided by 2, right? Well, that's going to be, what, 1.5? All right, what's 24 divided by 1.5? Boy, if only we knew how to do that. 24 divided by 1.5 is 16. All right, so at that point we could say that A works, right? A shows me that the associative property does not hold true for division. Okay, if I look at like B, just so that we see how this works, 3 divided by 6 is a half. 18 divided by half is the same as taking 18 times 2, right? Right, 18 times 2 is 36, correct? All right, 6 divided by 3 is 2. 18 divided by 2 is 9. I mean, I'm pretty sure. Let me check this. 18 divided by 0.5. Yeah, it's 36. I would say that... Oh, okay, hold on. Because the associative property means that I'm not changing the order, I'm just changing the association. What did they do in B? Did they use the what property before they did the associative property? They did the commutative property and then the associative property. So that's not a good illustration of the associative property being used. Okay, let's see. Why isn't D a good illustration for why association doesn't work for division? On D. Why is that not a good reason to show that the associative property doesn't work for division? Because it's all subtraction. We get that now? Okay. All right, and let's see, 81 divided by 3 divided by, they're not changing anything here. 81 divided by 3 divided by 3, we'd already do that in order from left to right, and we're still doing that in order from left to right, so that's not going to change that number at all. Okay? Okay, number 6, which equation demonstrates the identity property of multiplication? McEwen, what do you think? A. The identity property of multiplication, A times 1 equals A. 6 has A for an answer. I believe that is correct. Very good. Okay. All right. Number 7 is probably one of our first examples, somewhat of a proof. Okay. Because it says justify each step. So whenever we're doing proofs, which you'll get into in geometry and maybe some in algebra too, you always start off on the left. We got 11 plus 6x plus 1. And on the right, so this is my statement. Over here is my reason. My reason here is given. My first statement is always given because that's what they've given me. All right? If I'm trying to solve this, let's see. What's the next step? All right, so you want to do 11 plus 1, but to show that, I actually need to move things around, correct? I would need to do like 6x plus 11 plus 1, right? Right, and that would be what property? What allowed me to do that? Okay, so commutative property of addition. All right, now the next, and we can do a lot of this stuff in our head, but on paper we have to show it. So because of where 11 and 1 are, should I do those first according to order of operations? No. Right? Technically, I should have to do the 6x plus 11, right? But can I actually add those things? No. So what I actually need to do is 6x plus 11 plus 1. What property did I use there? Somebody who's not Tiffany. Distributive property. No, not the distributive property. Say that a little louder, Caden. Associative what? Property of addition. There you go. Okay, associative property of addition. Then the next thing I can do is now I can actually add those together, right? All right, and I get 6x plus what? 12. And all we're saying there is that we just added. Okay? Simple enough? Okay, so that's what our proof looks like there. All right, do we feel like we've got a pretty good handle on this? All right, I will let you go. I'll shut down the video and let you guys get to work.